So I want to talk about the addition rule and what that is all about. And I'm going to use as examples to demonstrate the addition rule, I'm going to use what you call problems 21 to 26. So the problems actually begin on page 158, but the chart that we need is on page 157. And so I'm going to go ahead and try and reproduce that chart on my paper for you. So it says we have men and women. And then the question up above is, was the challenge to the call successful? See, this is not a courtroom case. Do you know what this is? Did you guys read the blue? A tennis court. That's what kind of court this is. So what's the deal on the tennis court? What are they challenging? Yeah, is that ball in or out? Well, see, nowadays, you can use the Hawkeye electronic system for instant replay. I never heard of this in my life. I do like tennis, but I never heard of this thing. But apparently, you can do instant replay if you're in a professional tennis match. Tennis players here? All right. Well, anyways, is the ball in or out? So if it's in and you think it was out and you want it out, you can challenge. You can say, hey, check instant replay. Was the challenge successful? Well, for men, and then there's two possibilities, of course, right? Yes or no. Okay, so for men, the data in USA Today said 201 times the challenge was successful. 288 times the challenge was not successful. For women, looks like they didn't challenge as much, did they? But they did challenge. And 126 times the challenge was successful. They reversed the call. 224 times the challenge was not successful. So it looks like most times when they check the instant replay, they don't reverse the call. Right? I can see that from the chart. You guys with me? Okay, so we want to go to the next page where we can answer some questions. 21 through 26. Oh, by the way, a couple things going on here. Let me do 22 with you, because that is the problem I wanted to start with. Problem 22. It says, if M denotes I kind of want to do that later. Well, that's okay. If M denotes the event of selecting a challenge made by a man, find P of M with a bar over it. Okay, so I'm going to introduce some notation here. You know, it'd be nice to know, first of all, that we have data here. If I want to compute a probability using classical probability, you know what I'm going to do first, before we do 22? I'm going to compute the probability of M, where M is the event of selecting a challenge made by a man. Now remember, my formula for classical probability is you need the size of the event over the size of the sample. How do I get the size of this sample? How much data do we actually have? I have to add all those numbers up, right? Yeah, because they didn't do it for me. So I guess I have a little work to do. All right, so I'll do it. So you guys said 800 some? All right, let me see that. 201 plus 126 plus 288 plus 224. That is, yeah, 839. That is what in this fraction? That's the size of the sample. That's the denominator. Remember, denominator down, right? So 839, right? Okay. Now, what's the size of the event? Well, you have to understand what the event is. It says M is the event of selecting a challenge. See, they didn't say this in the book. They really should have said randomly selecting a challenge, meaning you're going to pick one of these challenges randomly. They're all equally likely. You guys with me on that? What's the probability that the one you pick is by a man? Let me ask this. Is it going to be more than 50% or less than 50%? Why more? They challenged more, right? You guys follow that? So more of the challenges were made by men. Okay. So the probability of M, how do I get the size of the event? What do I do? Add the men's numbers, right? 201 plus 288. And so we get 489 over 839. And so the probability of M happening is 489 divided by 839. Yeah, 0.583. That's 3 significant digits. M in the problem is where they told me. It doesn't normally stand for anything. But because it's a capital letter, it's an event. So they had to tell you what it stands for. Here it says, M denotes the event of selecting a challenge made by a man. They could have put P of W for, they probably would have. Matter of fact, that leads me to my next point. Let's compute P of W. Why don't you guys do that? So here, I'll do a different color. I'm going to say W is the event of randomly selecting a woman, or a challenge made by a woman. So a woman's challenge. Okay, let's do it. P of W equals, how'd you get that? How'd you get 350? So you added these guys, right? So that gave me 350. And so you did 350 divided by 839. Notice the size of the sample is the same. And Kate, what was that decimal again? Okay. Tyrone has a hand up. Did you guys notice that? See, Tyrone said he could get the answer without doing what Kate did. Right? Explain that again. What'd you do, Tyrone? Yeah. 1 minus 0.583. Right? Let's do that. If I do 1 minus 0.583, I get 0.417, which is exactly what Kate got. Does that make sense to you? Because something has to happen. So it's either you pick a man or you pick a woman. That's the only two possibilities. Now notice, Tyrone's idea works if you have two possibilities. You guys follow that? But yeah, this is going to be also probability of W. Now, oh, Kristen. Okay. Let me think of it this way. What would be the probability that we get a man plus the probability that we get a woman? Well, this is some fraction, right? Actually, it's 58.3%. And this is some fraction, which Kate computed was 41.7%. And if you add those up, 0.583 plus 0.417, what do you get? It's 100%. That's right. We get 1. Right, because it's 1.00. So if I write it as a percent, it's 100%. That's exactly right. I should have written the 0.00. Yeah. Yes. Every probability has to be from 0 to 1. If we add up all the possibilities, the probabilities for each of the possibilities, it must add up to 1. And that's an important fact. And that's what I'm using here to do Tyrone's shortcut. Kate?
Is this still relative frequency? Like, is it still flexible possibility?
Oh, okay, so that's a good question. Let me think.
It's not like it's a large number for the men.
Yeah, these are, right, these are relative frequencies here, aren't they? Right? So I am getting these probabilities from relative frequencies. But the ideas work the same. The idea that something has to happen is true in either case, right? And the idea is that probabilities can only be between 0 and 1. That's true in either case. And your book, next, is going to tell you what this means, M bar. And they will define M bar. So where am I going to write it? Because I'm running out of room. I don't want to go to the next slide yet, though. Here. Up here. M bar is what is called the complement of event M. M bar is an event also. It's the event that M does not occur. So it's like the opposite, in a sense. But in this example, it's very easy. If M doesn't occur, what does occur? M bar or W. Isn't M bar the same as W? If you don't pick a man, what do you pick? Right. So the answer to problem 22, I will tell you. What is the probability of M bar? It's 0.417. How do you get it? How do you get it? Well, either you figure it out the way we did it first, or you use this little formula that your book's going to give you. The probability of an event M will always be, the probability of an event M bar will always be 1 minus the probability of what? M. And I don't know that that formula would mean anything to you until you see the example. But you see the example, you're like, oh, I get it. If M doesn't happen, what's the chances of that? It's 100% minus whatever the percent was I had. So I did 100% minus 58.3%, and that gives me 41.7%. You guys get that? Good. I still haven't given you the addition rule, but we're on our way. This is good. Let's take our 10-minute break, okay? Then we'll come back. Let's see, what page is this? 158. Yeah, so on page 158, we're going to do another tennis replay problem. Problem 24 is the next one to try. There we go. Problem 24. Work on that using the table for a minute or two. First of all, you might say, what are we trying to find? Now, I'm going to use the same shorthand we used before. W was the event that we select what? A challenge of a woman, right? I guess I should put the whole chart up here again. What were those numbers? Let me get those numbers again. Okay, so there were men and women. And there were yes and no. 201, 288, 126, 224. And what was N, you guys? The sample size? 839. Okay, so there's the event that we select the challenge of a woman. Now, it says I want to compute the probability that, now what are we computing? It says, and I'm going to read carefully, the probability that the selected challenge was made by a woman or was successful. And you notice the word, W or. Now I guess, let me use another letter. I'll use S, because they use that in problem 21. S is the event that we select what? A successful challenge. Okay? So we want the probability that W or S happens. Now that is different from the probability that W and S happens. These two words are very different. Do you guys understand that? If you don't, what's that? No? No? It asks for this. This is what they want. This is problem 24. Why am I bringing this up? Because it's going to be important as we move, well, to the next section for one thing, but even now, I want to be very clear about what the word or means. And I think the only way to do that is to first of all tell you what I mean by and. Let's compute the probability that W and S both occur. Well, I know it's going to be something out of 839. Do you guys know what it's going to be? Look at the chart. When I say W and S, that means that the challenge I pick was made by a woman and was what? And was successful. The only place that I have successful challenges by women is right here in the chart. So the probability of W and S occurring would be 126 out of 839, whatever that is. I don't care right now. I want you to understand the probability. Does that make sense, what and means? And means I want to be in both columns. Now, here's the question. What does this mean? W or S? That means, well, again, 839 is our sample space. Where do I want to be on the chart? Well, for W or S, see, this is still okay. But there's other places you can be on the chart and still be okay. Like here. What happened in this situation? That's where the woman challenged, but what happened? It was unsuccessful. But we are going to include that when we compute probability of W or S, because that's W happening. You guys follow that? And we're also going to include what? We're going to include, which one? Let's see. Probability of women or successful. What if a man makes a successful challenge? Are we including that in this problem? Yeah. Matter of fact, the only thing we're not including is when it's a man and unsuccessful. See that? So the answer you want, you would get by doing 201 plus 126 plus 224 over 839. That's what I mean by or. I mean either one of these happens. Okay? Now, what was the name of this section? The addition rule. I'm going to write down for you the addition rule. We haven't used it yet, really. But here's the addition rule. The addition rule is what you do if you need to compute the probability of A or B happening. Two different things could happen, A or B. That's kind of what we did, right? Here's how you get it. It's called the addition rule because it's probability of A plus, guess what? Probability of B. And that almost works, but not quite. You have to subtract something. A different probability. Oh, we'll get to it in a second. Hold on, hold on. Here. Remember on the last slide, didn't we compute probability of W happening? What was that? Wasn't it 40-some%? 0.417? Okay. And by the way, if we had done exercise 21, I think we would have computed probability of S. I'll do that right now. Let's see. So successful, that's this. That's 201 plus 126 over 839. What I really need is the decimal. So let me calculate that. 20, oops, turn it on. That would help. Okay. 201 plus 126, enter, and then I want to divide by 839. So I got 38, well, about 39%, 39.0%, if you round. Okay, so there's the probability of S happening. Now, I'm going to use that addition rule to compute probability of W or S. Need a blue pen. Here I go. The probability of W or S, according to my rule, is the probability of W plus the probability of S minus something. Some other probability. All right. So let's see. The probability of W was 0.417 plus the probability of S happening, what's S? 0.390 minus something. All right, let's see what it is. Well, pull that calculator back out. By the way, W or S here, we didn't compute that decimal, did we? I'll do that now. Let's see what it actually is. We know it's 201 plus 126 plus 224. That's the numerator. 551 out of 839. Okay, so that's 0.657. Oh, wait a minute. Do you see why I have to subtract something? This is 0.657, but if I just add W and S, do you see how that's no good? Because what am I going to get? I'm going to get like 0.7 something or 0.8 something. It's too high. What do you have to subtract? Well, that's best explained, I think, by the good old classic. What's this called? Well, they are called circles. MasterCard? No, not MasterCard. Venn diagram. Yeah, it's like MasterCard. Okay, so this is event A, and this is event B. And if you compute the probability of event A, it's kind of like you're doing this. You're saying, okay, I'm going to compute this probability. And if you compute the probability of event B, you're saying, okay, I'm going to compute this probability. What's the problem? They overlap. There was some stuff we counted twice, right? By the way, the stuff you counted twice actually has a name. You might call this part in here, the intersection, you might call that A and B. Because that's where, if you're in there, you're in event A and in event B. Does that make sense? So you know what you have to subtract? A and B. There's the addition rule. The probability of A or B happening will be the probability of A plus the probability of B minus the probability of A and B happening. Cool. So now, what do I have to subtract? In my example, I have to subtract the probability of W and S happening. Did I compute that already? I guess I didn't write down the decimal. You say it's 0.150? So if this is 0.150, then when I subtract it, let's see what that gives me. Does it give you the 0.657? It has to, right? There it is. Okay. And again, it's because there's something that got counted twice. Let me show you on the picture, no, on the graph, what happened. Do you guys see the blues that are circled? The 201, 126, 224, right? You guys see that? Okay. Let me walk you through this. When I computed probability of W, what's that? There it is. It's that part right there, right? That's 126 plus 224 over 839. When I computed the probability of S, S means successful. Where am I in the picture? This stuff, right? So that's 126 plus 201 over 839. Do you see how something got counted twice? What got counted twice? 126 over 839. So the addition rule says, yeah, you can add them for an OR problem, but you have to subtract what you'd get if it said and. And then you get the right probability. I think that's pretty cool. Shelley, question? So this problem, not in the book, made up. Okay, suppose I know the following. The probability that the Browns win next week. Suppose I know the probability that the Browns win next week is I'm a fan, 65%. 0.650, 65%. The probability that it rains a lot, I'll just say it rains. That's going to help the Browns win, by the way. Help the running game out because we've got to go through the mud. The probability that it rains, suppose I know there's a 70% chance of rain on Sunday. In Denver, by the way. Okay, let's compute the probability that the Browns win or it rains. That's kind of a weird thing to compute, but I could do it. For shorthand, let me say that B is the event that the Browns win. And let's let R be the event that it rains. And then what am I doing? I'm computing what? B or R. for R. What does the addition rule say that's going to be? Probability of B plus the probability of R minus the probability of B and R. Now again, that's kind of weird. Well, that's a good question. Would it be 0? Do you think the Browns could win if it rains? They could, right? Now again, I'm making this up, right? I don't know any of these probabilities for real. If I did, I probably wouldn't be a math teacher, right? I'd be doing sports forecasting, or else I'd dig over for Dick Goddard if he ever retires. One of the two. So, what I'm saying is that if I want to compute the probability that one of these things happens, I could get it by doing 0.650 plus 0.700. But notice that's not good enough. By the way, what would you get if you added right now? You get over 1. That's bad, right? Yeah, so that's not going to work. Do you see what I'm saying, Shelley? If I also knew the probability that the Browns win and it rains, now suppose I know that that's 0.710, because they're better in the rain. Now if I knew that, I could subtract 0.710, and I'd get the answer. It's 0.640. All right? Does that help or hurt? You need all this information to get it, don't you?
So there's nothing we have to use that to get something else, like the complement of we or the constant.
Okay, now we've got a lot of people talking at once, so this is all... Okay. What I'm telling you is sometimes I know the probabilities. In this example, I don't really know those probabilities. I made them up. Okay? Sometimes I know the probabilities from theory or from something else. In the example we did, we knew the probabilities because we were randomly selecting data that we knew a lot of stuff about. We had a whole chart about it, right? But you don't need the chart to do the problem. You can actually use the rule if you have these probabilities. That's what the addition rule says. David?
No, for the last hand, the Browns win and it rains.
Yes.
Now, is that just completely different? How do you come up with?
Yeah, how did I come up with any of this? Well, I was pretending to be the coaching expert that knows that the Browns do better when it rains. But yeah, I don't really know. No, it doesn't matter what the numbers are. The formula works. Why does the formula work? I think the best explanation for why it works is this picture. Because if you just count A and add it to B, you counted part of it twice. You counted A and B twice, so you have to subtract that off. Is that okay? One more question. David.
So, for like that last part, it'll always be something different. It's always going to be like the 0.1 and the 0.710.
Yeah, I hate the word always, but I hate the word most of the time. I hate the word sometimes. All I'm going to say is that the formula works. If you know 3 of these guys, you can get the 4th. How about that? If you know these 3, you can get the 4th. You know what a big deal is, though, guys? And this brings me to really the next lesson, which is the last thing I'm going to do today with the last 10 minutes. See, it's important to be able to compute the probability of A and B. Do you guys get that take-home message? If you don't have this, can you use the addition rule at all? No. So, question. How do I compute probability of A and B. How do I compute it? Answer. Multiplication rule. Multiplication rule. So that brings us to the next section.